Okay, so in the last video, we saw that in this for this operator, we weren't able to use a linear um, decision boundary in order to classify this properly. What this picture was about was that you can take the same operator and recast it with this, and actually, I think one of these points collapses into, sorry, two of these dots collapse into one, and so you can. But anyway, the idea is that maybe using a more complicated neural network instead of just one neuron, maybe we can achieve more robust or more interesting results. So we're going to talk now about multi-layer neural networks and multi-neuron layers. So we have this rather complicated looking picture, but we have to break it down. So we have here the same input layer, x1, xj, xd, and so on. And before we just had this one neuron. So what we're suggesting here is adding some other neurons to this to the network, and later on we're going to do this. Here we have what we call this one hidden layer, and then next we're going to have multiple hidden layers. So this layer and this layer we'll refer to as the hidden layers. But let's talk about one hidden layer first. So this is called a fully connected network, because basically, in the sense that this neuron receives inputs from all of these. So sometimes we don't do it that way, but in this case we are. This neuron also receives inputs from all of these. This neuron also receives inputs from all of these. So we can talk about this one. Gets input into all of these and has weights that modify that input. So in other words, there's a weight here. You can see this gray arrow here. There's a weight here. There's a weight here, and so on. And then the same thing with this one. There's a weight here. There's a weight here. There's a weight here, and so on. So we have a lot of weights, and basically those weights can form, in order to write them in an organized way, they can form a matrix. So we've referred to a weight as W sub ij. Now, I believe, I forget actually, but I think that basically, I don't remember, but I think we would just want W to be the matrix, and when we have I, comma j, really we're referring to the individual elements. But anyway, so let's imagine that it's this capital W is made up of a whole lot of entries. So we can talk about the ijth entry. So let's read this highlighted part here. Small w sub ij, and then 1 just means that it's the first layer. As I said, we just have one hidden layer so far. But later we're going to have several hidden layers, so we'll have like a 2 for the second hidden layer. So, but anyway, w ij is being used to indicate the weight going into the ith neuron. So this is the target is the I, and coming from the jth input. Okay, so here wij means this is the first neuron, so that would be w1, and coming from this input would be w11. Coming from going to here, but coming from here would be, let's say this was 2, the second one. So it would be W1, 2, and so on. So that's the way these indices work. So the J stands for where it's coming from, so it's coming from here. And the I stands for where it's going to, so it's going 1, comma 2. So that's that notation. And again, this 1 here means for the first layer, but we'll see later that there's a W2 here and W3 and so on. So, okay. Now, we did say what we're going to also have, besides just multiplying. So, in other words, we're going to take this input here, we're going to multiply it times W. In this case, it would be called W11. But then we're also going to add a B. Remember, we also talked about a B, a constant term, basically. And so that is going to, since there's going to be one B to be added in here, and another B to be added in here, and another B to be added in here, that's going to be also actually a vector. So we write the B as a vector. So it's it's bold B, and it's a bold W to indicate that it's actually a matrix here. And X is also a vector of inputs. Okay? Now when we multiply this times this, we get a vector. And then when we add another vector to it, we get another vector. And so what we're getting is we're outputting a vector here. And that vector is just the input that goes into here, the input that goes into here, the input that goes into here. Notice again that the input that goes into here comes from many different places, but it's a single value in the end. And the input that goes into here, again, same thing. So anyway, we have this stands for the inputs into these. So this is a vector. The first element of that vector is the element that goes in here, is the value that goes into here. The second element of this vector is the value that goes into here, and so on. Well, dot, 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 so I don't know. Anyway, okay. Then, now we have what's going in here. Now we're going to take an activation function like the sigmoid function or the hyperbolic tangent function, and we are going to apply. We're going to apply it. The element, the value that comes into here, we're going to take the activation function and apply it to that. The value that comes into here, we're going to take the activation function and apply that to that value, and so on. So we're going to apply the activation function to each of these. So the result of that is also going to be a vector, right? We're going to get an output here, an output here, an output here, and so on. So we're going to get lots of different outputs. So that means it's a vector, and that's what this is. The G is the activation, and we call this whole thing. So first doing the A, first doing all this stuff, and then doing the activation. We call that whole thing H. So in other words, we start with X, and we end up with some value. We call that whole process H. Okay? So we have this. What else? Anything else here? No. And then finally, so now we have the hidden layer. And now in this network, in this architecture, we just have one hidden layer. So now we are going to get the output, and we're going, so we have the hidden layer. Basically, it's putting something out here, putting something out here, putting something out here, right? That's the G is the activation. So it spits out something here, it spits out something here, it spits out something here. That's what this is. That's what H is. And then, and H is a vector again. And then finally, we're going to have a set of weights applied to that. And we are going to add, again, we're going to allow for a bias vector B. And that's going to go into here. And then we're going to output from here something else. So we're going to use a special function, special symbol for the last layer, the output layer. So we might have many input layers, and we'll use basically G and H for all of those. But for the last one, we're going to use a special symbol just to indicate that it's the last one that's going to be the output function. So we're going to take all this stuff inputs into here, and then we're going to take another function, we'll call it O, and apply it to that. So this is all the stuff that comes in, and then O acts on that, and we get something out at the end. Okay? And that whole thing is going to be called f of x. And this can also be a vector.